Welcome to today's deep dive. We're going to try to unpack the really fascinating history behind something you probably see every day. Two little numbers, 50 hertz and 60 hertz. You know, those standard power frequencies that we use all around the world.
Right.
And trust me, there's way more to this story than you might think. We got some awesome academic papers and some really interesting historical articles to dig into today.
Yeah, it really is amazing how these numbers that just kind of seem mundane and in the background actually have this whole backstory of technological, breakthroughs and fierce competition and just global oddities. It's a really fascinating story.
So to kick things off, let's go way back to the very beginning of AC power systems.
Okay.
And our sources are talking about this like wild west of frequencies.
Yeah.
Like there was 16 and 2/3 hertz, 133 and 1/3 hertz.
Oh, wow.
Can you imagine like living with that?
I mean, can you imagine like trying to read a book under a 133 hertz light bulb?
Oh my gosh.
It'd be like a strobe light. It's fascinating how we ended up with 50 and 60. It wasn't like a grand conspiracy or a single decision. It was really a gradual evolution that was shaped by the technology of the day, economic factors, and just the need to standardize as these power grids grew larger and larger.
So one of our sources mentioned this pivotal moment. It's 1863, the first commercial use of AC power.
Okay.
It was in a lighthouse in France. Yeah. And they were using a 53 hertz system. What was going on back then?
So back then, the main electrical devices were arc lamps and some of the first electric motors.
Right.
And these things actually work best on DC power or lower frequency AC power.
But DC was tough to send over long distances, right?
Yeah, you're exactly right. Direct current was really difficult and expensive to change the voltage of for efficient transmission over long distances. So that's where AC power starts to become really attractive.
Especially with the invention of transformers.
Exactly. Transformers were a game changer. And guess what? Transformers actually work better at higher frequencies.
Oh, really?
Yeah.
So you've got like early lighting and motors wanting lower frequencies.
Yeah.
But then the transformers are pushing for these higher frequencies. Sounds like a real tough situation for those early engineers.
Yeah, it definitely created some tension. And then the invention of incandescent light bulbs throws another wrench into the mix.
Right, because I remember LEDs are pretty good.
Yeah, LEDs are great. They can handle a wide range of frequencies. But those old incandescent bulbs, they actually worked better at higher frequencies.
Oh, interesting.
Yeah, it helped to reduce that annoying flicker you would get with lower frequencies.
Okay, so now we have this three-way tug-of-war going on.
Yeah.
It's like the lighting, the motors, and the transformers are all kind of fighting for their ideal frequency.
Right. And then enters Nikola Tesla with his famous induction motor.
Right.
That really starts to tip the scales.
Yeah, because those motors were pretty important for industry and everything, right?
Absolutely. They quickly became essential, and they happened to work best around that 50 to 60 hertz range.
Okay, so it's starting to kind of narrow down a little bit.
Yeah.
Now things are starting to heat up. We've got two major players entering the scene.
Right.
We got Westinghouse in the U.S. and AEG over in Germany.
Yeah.
And they really shaped how this frequency battle played out.
Right. It was a time of fierce competition.
Yeah.
Westinghouse was really focused on lighting, so they chose 60 hertz to minimize that flicker.
Makes sense.
They knew there were some issues with motors, but they believed that technology would eventually catch up. On the other side, AEG started with 40 hertz.
Okay.
But they ran into a problem during their famous Frankfurt demonstration.
Wait, what was the Frankfurt demonstration?
It was groundbreaking. They transmitted AC power over 175 kilometers.
Wow.
It was a huge proof of concept that long-distance AC transmission was possible.
That's one way.
But during this demonstration, they noticed some really bad flickering with their 40 hertz system.
Oh, so it's like a public kind of mishap.
Yeah, you could say that.
Okay.
So they decided to bump it up to 50 hertz, and that became the standard in Europe.
Okay, so we've got Westinghouse over here at 60 hertz AEG, over there at 50 hertz.
Right.
But wasn't there another big player in the U.S., General Electric?
Yes. GE was also a major force, and this is where things take a turn.
Sure.
Initially, GE actually aligned with AEG and used 50 hertz. They even built a power plant in California based on that frequency.
Wait, so the U.S. had both 50 and 60 hertz systems running at the same time?
Yeah, for a while it was a period of transition and some confusion.
That's got to be a logistical nightmare.
It was. But this is where a brilliant engineer named Charles Proteus Steinmetz comes in.
Oh, yeah, I've heard that name.
He was working for GE, and he identified a problem with resonance in a 125 hertz system.
Okay.
And get this, He recommended halving the frequency.
So if they did that, they would have ended up really close to Westinghouse's 60 hertz.
Exactly. It's a real what-if moment in history.
Wow.
But remember, this was a very competitive time. GE was facing pressure from Westinghouse, and they needed to standardize.
So they switched to 60 hertz.
Exactly. In 1894, they made the switch to maintain market share.
So it sounds like market forces really played a big role in cementing 60 hertz as the standard in the U.S.
Yeah, they definitely did. But it makes you wonder, why didn't everyone just agree on one frequency from the start?
Yeah, that would have made things so much easier.
It seems obvious now, but back then, different companies were innovating rapidly and pursuing what they thought was best.
Right.
There was also very little international collaboration on these standards.
Makes sense.
Yeah.
It's amazing how these early decisions had such a lasting impact on the world.
It really is. But there is one interesting exception to this 60 hertz versus 50 hertz divide.
Oh yeah, what's that?
Japan.
Japan. What happened over there?
Well, remember those two Japanese engineers we talked about earlier?
The ones who traveled the world?
Yeah, they were looking for the best electrical technology, and they ended up bringing back both 50 hertz and 60 hertz systems.
So they have both.
Yeah, thanks to separate installations by AEG and GE.
Oh, wow. So Japan is running on two different frequencies.
To this day, they have this split system. It's incredible.
How do they even manage that?
It's quite a feat of engineering. They have these 4 massive frequency converter stations.
Wow.
That link the two grids together so they can share power across this frequency divide.
That's insane.
It is.
Speaking of engineering feats, one of our sources talks about Southern California Edison.
Yeah.
They had to convert their whole system from 50 hertz to 60 hertz back in the mid-20th century.
Oh, wow.
It took them over 20 years.
Can you imagine the logistics of a project like that?
That's crazy.
It really highlights the challenges and costs involved in switching frequencies once a system is already in place.
Yeah, it makes those early decisions by Westinghouse, ADG, and GE even more significant.
Absolutely. It's like they set the electrical course for generations to come.
It's incredible.
Yeah.
There's still more to uncover, right?
Definitely. In part 2, we'll delve deeper into the nuances of these frequencies and explore why some systems still use different frequencies today.
Okay, so buckle up, listeners. Our journey through the world of power frequencies is just getting started. Welcome back to our electrifying deep dive into power frequencies. You know, before the break, we were talking about how hard it is to change these systems once they're already set up.
Right.
I mean, 20 years for Southern California Edison to switch over? That's incredible.
Yeah, it was a massive undertaking.
But it makes me wonder about those systems that didn't switch over. You know, the ones that still use those kind of outlier frequencies today.
Yeah, that's a great point. It's easy to think that 50 and 60 hertz are like the only frequencies that matter.
Right.
But that's not really true. There are certain applications where other frequencies actually make more sense.
Like you mentioned, aircraft.
Exactly. Aircraft are a perfect example.
What's so special about the frequencies they use?
Well, in aircraft, weight is everything.
Right. Every pound you can save.
Exactly.
Yeah.
It all adds up to better fuel efficiency and performance.
Okay.
And this is where our earlier talk about transformers comes in.
Oh, yeah. You said that transformers work better at higher frequencies.
Exactly. So by using a higher frequency like 400 hertz, which is common in aircraft, they can use smaller and lighter transformers and motors.
So it's all about finding that sweet spot between performance and keeping things lightweight.
Precisely.
That's fascinating. What about those railway systems that use lower frequencies? I remember reading about 25 hertz and even 16 and 2/3 hertz systems. Why those odd numbers?
Those lower frequencies are often linked to older railway systems that use really big, powerful motors like electric locomotives.
Right.
And those motors tend to run more smoothly and have less wear and tear at those lower frequencies.
So even though 50 and 60 hertz kind of won the frequency wars,
right,
there are still these niche areas where other frequencies are just better suited.
Exactly. It's all about using the right tool for the job.
It's a good reminder that engineering isn't always about finding a one-size-fits-all solution.
Absolutely. And it's not just about the technology itself, but also this historical context. I mean, these older railway systems were built with those specific frequencies in mind.
Yeah.
And trying to convert them now would be a huge and expensive project.
Makes sense. Speaking of historical context, our sources really highlight some of the key players who shaped this whole frequency landscape.
Yeah.
Like Charles Proteus Steinmetz, the GE engineer, who suggested having that 125 hertz system.
Yeah. Steinmetz was a true visionary.
He sounds like it.
His work was so important in helping engineers understand and design efficient AC power systems.
Really a pioneer in the field.
Absolutely.
Oh.
He was a master of math and analytical techniques.
It's amazing how his work back then still has an impact on us today.
It really is. And when you think about it, the standardization of power frequencies was a huge achievement.
Yeah.
It allowed us to connect power grids across vast distances, which led to more reliable and efficient electricity.
Can you imagine our lives today without reliable electricity?
It's hard to even fathom.
Everything we do relies on it.
Yeah. From the lights in our homes to the devices we use to connect with each other, it's all powered by electricity.
And those decisions made over a century ago, about 50 hertz and 60 hertz, are still influencing us today.
It really highlights the importance of standardization in technology.
Yeah.
Once a standard takes hold, changing it is incredibly difficult and expensive.
As we saw with Southern California Edison.
Exactly.
Which brings me to a question I've been thinking about. What does the future hold for these power frequencies? Are we stuck with 50 and 60 hertz forever?
That's a question that's being debated right now, even among the experts.
Really?
Some people think that new technologies like high-voltage DC transmission and microgrids could challenge the dominance of 50 and 60 hertz.
Wait, high voltage DC?
Yeah.
But didn't AC win the current wars a long time ago?
It did, but technology is always evolving.
Right.
High-voltage DC has some advantages for long-distance transmission, especially when it comes to renewable energy sources.
Like solar and wind.
Exactly.
It's also more efficient for transmitting power underwater, which is becoming more important as we explore offshore wind energy.
So you're saying we might see a comeback for DC?
It's definitely a possibility. And then there are microgrids.
What are those?
They're basically like mini power grids
Okay.
that can operate independently or connect to the main grid.
Hmm.
They offer more flexibility and resilience, especially as we move towards more distributed energy generation.
I can see how that would be beneficial with the growing focus on renewable energy and energy independence.
Absolutely.
But wouldn't microgrids potentially operate at different frequencies?
Yeah, it's possible that they would optimize their frequency for their specific needs.
Wouldn't that create new challenges?
It could introduce some complexity, but it also presents an opportunity
Okay.
to rethink how we generate and distribute electricity. Maybe it could lead to a more efficient and sustainable energy future.
So while 50 and 60 hertz have served us well for over a century,
Right.
the future of power frequencies might be a lot more diverse and adaptable.
Yeah, it's exciting to think about.
It really is a reminder that technology is constantly evolving to meet the changing needs of our world.
Absolutely. But before we get too far ahead of ourselves, there's one more fascinating aspect of this power frequency story that we haven't touched on yet.
Oh, there's more?
There is. It has to do with time.
Time.
Yeah, and how the precise control of power frequencies actually played a crucial role in our ability to measure time accurately.
No, that's intriguing.
Yeah.
I'm all ears. All right, I am totally hooked. You took us from flickering lighthouses to clocks. And now you're saying there's a space connection. I got to hear more about those exotic power systems in space.
Well, get ready for blast-off, because we're going to the final frontier of power frequencies. You see, in space, weight is even more crucial than it is in aircraft.
Yeah, makes sense. It takes a ton of energy to launch anything into space.
Exactly. Every ounce matters. And just like in aircraft, higher frequencies help reduce the size and weight of those power components.
Okay.
But there's another big factor in space: radiation.
Radiation, how does that affect things?
Well, space is a pretty harsh environment. You've got all kinds of radiation flying around that can really mess up electronics.
Right.
So space-based power systems have to be super tough and able to withstand that radiation.
So lightweight and radiation hardened. That's got to be a challenge.
Yeah, it definitely creates some unique engineering hurdles, but engineers are clever. They've come up with some amazing solutions.
Like what?
Well, one approach is to use even higher frequencies than those in aircraft.
Higher than 400 hertz.
Oh, yeah. Some spacecraft power systems operate at frequencies in the kilohertz or even megahertz range.
Kilohertz, megahertz. Wow, those are some seriously high frequencies.
They are, and by going that high, they can shrink those transformers, inductors, and capacitors down even further.
So it's all about making those components as small and light as possible.
Exactly. Every gram counts when you're trying to get something off the ground and into space.
It's amazing how pushing the limits for space exploration can lead to breakthroughs that benefit other areas too.
It really is. It shows how interconnected science and engineering really are. And the story of power frequencies in space doesn't end there.
Really? There's more.
Yeah, some missions have even tried out entirely different types of power systems.
Like what? I'm really curious now.
Well, NASA, for example, has been looking into solar dynamic power systems.
Soul dynamic, what's that?
For longer missions, they use concentrated sunlight to heat up a special fluid, and then that hot fluid drives a turbine to make electricity.
So instead of using solar panels, they're using heat to generate power.
Exactly. And solar dynamic systems have some serious potential. They could be really efficient and reliable, especially for missions that need constant power.
That's pretty incredible. It sounds like the future of power in space is going to be as diverse and innovative as the missions themselves.
I think so. As we explore further into space and push those boundaries, we're going to keep developing new and amazing power technologies. Who knows what we'll come up with next?
It's mind-blowing to think that something as simple as the frequency of electricity has had such a huge impact on our technological world. We've gone from flickering lighthouses to super precise clocks to powering spacecraft. It's a story that connects us all.
It really is. And it's been a blast exploring this journey with you and our listeners. I hope everyone listening has a new appreciation for those little numbers on their appliances. Those frequencies represent a long history of innovation and the constant pursuit of progress.
Absolutely. And to everyone listening out there, thanks for joining us on this deep dive into the world of power frequencies. We'll see you next time. And until then, keep those minds curious. There's always more to discover.